So yeah, I don't know the exact composition of this audience, but I think this talk is supposed for non-specialists. So if you are working on quantum antibody systems, maybe what I'm going to tell you is maybe kind of too easy. But anyway, so as a condensed matter theorist, I'm interested in a system like solid electron system, which consists of enormous number of particles like electrons, and they move and interact with each other. Also behaves quantum mechanically. So if you try to do the brute force calculation, the dimension of the Hilbert space is exponential of some enormous number, so it's really huge. So it's, except for some special exactly solvable systems, usually it's hopeless to solve this kind of system exactly. But of course, we have been, collectively, human beings have been trying to understand and predict properties of this kind of system using various approaches like a perturbation theory and computational approach. And of course, if you do computational approach, then usually you can only deal with finite size systems, but then you try to extrapolate to infinite system size, Soundline limit. So there has been great progress on these approaches in the last several decades, but in general, this kind of problem remains very challenging. So, but there is very conceptually and practically very powerful framework, which is basically the renormalization group. So we start from microscopic models like electron models on the lattice, or even more faithful model to realistic material anyway. So then, as I said, usually it's very difficult to handle these microscopic models directly. But then you can apply the idea of renormalization group. Then at least in principle, you can derive low energy effective theory. Then, yeah, this is basically quantum field theory. So you can gain a lot of insight from this effective theory and make many predictions. So this approach was initiated by late Ken Wilson. But so this is conceptually very nice and powerful and also useful. But actual calculation of this renormalization group, if you have tried, is rather challenging and often involves some approximation or ansatz. So then what is often useful is some sort of universal constraint, which put very strong constraint on the low energy effective theory, which you can derive from these microscopic models using some symmetry, based on symmetry and so on. So this is useful to test your theory, low energy effective theory. You can try to derive this low energy effective theory, but in general, you are not completely sure if this is right. Then you can compare with the universal constraint. Then you can check your theory. And also, this universal constraint can be useful as a guiding principle to find an interesting system and predicting new phenomena. So then part of the title of my talk says thought experiment. So probably you are familiar with this, but let me mention one very interesting example. So for many centuries, of course, people knew that if you leave some object, then it falls down to the ground. But then after Aristotle in Western world, and also in other parts of the world, I guess, but for thousands of years, people believed that the heavy object falls faster and the lighter object falls slower, because if you make a naive observation of daily phenomena, then things looks like it. But then, as you know, Galilei came up with some idea That is what happens if you connect this heavy object with light object. Then if you accept the idea that the heavy object falls faster, then this tends to fall faster, and this light object try to fall slower, then this heavy object must pull this light object. Okay. But on the other hand, if you connect these two objects, then you can regard these two objects as a single object. In that case, this entire object is even heavier than the original one. So it should fall even faster. So there's a contradiction. So that means that the naive idea that the heavier object falls faster must be wrong at some point. Now, of course, this argument alone does not exactly predict Newtonian mechanics or anything, but still this is very powerful. It shows some problem with very, very old idea which survived like 1,000 years. So I want to use this thought experiment approach and apply this to quantum anybody. And yeah, in history of physics, there are many other examples of thought experiment which lead to powerful conclusion. But let me skip this. So in my talk, I want to focus on a model of electron or some atoms in this quantum many-body problem, typically like a Hubbard model. So I consider, for example, this square lattice. It can be more general lattice, but let's consider this square lattice. And then each side can be empty or occupied by particle. And if this site is occupied by particle, then this particle can hop to the next nearest neighbor. So this hopping can be represented by this term in second quantized notation. And usually we introduce some interaction like interaction between nearest neighbors. If both the nearest neighbor sites are occupied, there is an extra energy. So this is a typical Hubbard type model for spinless fermions or bosons. But you can introduce spin degree of freedom, flavor, or whatever, consider more complicated lattice. But yeah, basically, I want to discuss systems like this. And for simplicity, I assume that this system has a lattice translation invariance. And also for simplicity, I impose a periodic boundary condition. Then the thought experiment I want to make is so-called flask insertion. So that is, I consider the square lattice, but impose a periodic boundary condition in both x and y directions. Then topologically, the system is equivalent to torus, as you know. Then this torus has a hole. Of course, electron can hop only on this two-dimensional lattice. So electron cannot see this hole, but topologically there is a hole. Then you can insert a magnetic flux in this hole. Then initially, let's say this magnetic flux was 0, and then you increase this magnetic flux. Yeah, then consider what happens. So this is already known in classical electromagnetism. That is, if you include this flux, there is so-called electromagnetic induction. That is, increasing this flux induces electric field in x direction, so this direction. And induced electric field is proportional to the time derivative of this magnetic. Then first, I want to discuss what happens to the total momentum. So in the lattice system, you don't have a continuous translation symmetry. So you have to take care about what kind of momentum it comes out. So as you know, in the continuous space, momentum corresponds to infinitesimal generator or translation. But on the lattice, there is no infinitesimal translation. But there is a translation by one lattice site. Then you can define the so-called total crystal momentum in this way. That is exponential of I times this total crystal momentum is lattice translation by one side in x direction. So this is nothing but the total crystal momentum. But from this definition, you can easily see that this total crystal momentum is well defined only modulo 2 pi. So this 2 pi equivalence corresponds to so-called Brillouin zone, well known in solid state physics. Anyway, so then I want to introduce a flux and increase this flux time as a function of time. So for that, I need to introduce a vector potential in this lattice model. So originally hopping term in the Hamiltonian looked like this, but then now this hopping must be coupled with gauge field, a vector potential like this. And this vector potential in x direction is nothing but magnetic flux phi divided by system size in x direction. So there is a gauge ambiguity or freedom of choosing various different gauges. But for simplicity, I choose so-called uniform gauge. So this, I have vector potential only in x direction, but it's uniform everywhere. So in that case, even after introducing this vector potential, since this vector potential is uniform everywhere, my Hamiltonian, including this vector potential, is still invariant under lattice translation. But this lattice translation operator is directly related to this total momentum. And from this, you can write down the Heisenberg equation of motion for this total momentum. Then dpx over dt can be related to this commutator, which vanishes. So actually, the total momentum doesn't change over time, even if you introduce this vector potential, even if you change this vector potential as a function. So it implies that the momentum is unchanged by flux insertion. But this sounds strange because if you insert a flux, then you induce an electric field, and electrons have electric charge. So these electrons must be accelerated by applied induced electric field. So it sounds like a contradictory, but it's of course not real contradiction, because the resolution is that the px I just defined corresponds to so-called canonical momentum. So in the continuous space, this is like a derivative by x, but it's not gauge invariant in the presence of gauge field. So canonical momentum is gauge dependent. So you cannot directly compare gauge dependent quantity after and before flux insertion. So in order to make a meaningful comparison, you have to compare the momentum in the same gauge. So actually, if you insert a flux, and when this flux reaches this particular value 2 pi, or if you resurrect the Planck constant and the electron charge, which is Planck constant over E, then you can eliminate this gauge field, uniform gauge field AX by so-called large gauge transformation, which is explicitly given by this operator, which is a local phase change. But this local phase change is proportional to x coordinate of this system. And when you go around the system once and come back to the original position, then this phase twist becomes 2 pi. But the phase twist 2 pi is equivalent to 0. So this is consistent with periodic band equation. So if you apply this large gauge transformation, topologically non-trivial gauge transformation, you can eliminate the vector potential corresponding to this unit flux quantum. So that means that, so I start from some initial state. Let's say I started from ground state, which has some particular total crystal momentum. Then I do the flux insertion. But during this flux insertion, as far as you choose a uniform gauge, as I said, there is some evolution of the state, but momentum doesn't change because Hamiltonian is always translation invariant. So it sounds like after flux insertion, the total momentum didn't change afterward. But as I said, after insertion, you have a non-zero vector potential. But originally, you had no vector potential. So you cannot directly compare these two momentum because you are in different cases. So in order to make a physical comparison, you have to apply this large gauge transformation to eliminate vector potential to this final state. So after applying this large gauge transformation, the final state after gauge transformation should look like this. Ux times psi 0 prime is the final state. So now I need to find the total momentum of this state. And this can be derived rather by simple algebra, because this translation operator and this large gauge transformation operator has a particular commutation relation. So basically, Tx and Ux almost commute, but it doesn't quite commute because this Ux contains x coordinate. And if you apply the lattice translation, x changes to x plus 1. So Tx Ux and Ux Tx are different by this factor. You need to pick up this factor number operator from each side. And this seems to look like a non-trivial operator, but actually you find that this is a summation of particle number on each lattice side. So this is nothing but, this sum is nothing but the total particle number, which is conserved. Maybe I forgot to say, but I'm discussing the lattice model which conserves the number of particles, then this is a conserved number. So you can express this extra factor in terms of so-called filling factor, that is number of particles per unit cell, which is very useful quantity in solid state physics. So this phase factor is 2 pi times I times system size in y direction, Ly times this filling factor. So if you combine all these discussion, then what you find is that after this large gauge transformation, after doing the flux insertion and large gauge transformation, the total momentum of the final state is given by this. So that is initial value of the momentum plus this 2 pi times Ly times. So there is some extra contribution. So this represents the acceleration of electrons by electric field. But it's completely determined by the filling factor, nu. And this system size Ly you can choose at your will. So there are various applications of this result, so this universal result. So one of the consequences is that, so let's assume that this filling fraction is not integer, some fraction number. Then you can write this filling fraction as P over Q. So P and Q are some co-primes, integers without the common factor. Then I can choose this system size in y direction, Ly, to be a co-prime with this denominator Q. In that case, the momentum shift during this flux insertion is 2 pi times Ly times nu is some non-integer, 2 pi times non-integer modulo 2 pi. So that means that the final state must be different from the initial state. And this is very simple conclusion, but it has very powerful, it puts very powerful constraint on the possible phase of matter. Because, okay, so suppose the system is a trivial insulator without any feature, then usually you expect that the system has a gap and you have a unique ground state. And by gap, I mean all the excited states are separated from this ground state by gap. But if you insert a flux adiabatically, then this ground state should evolve into ground state. And if the ground state is unique, then after adiabatic flux insertion, ground state should come back to the same flux. But this shows that this is not possible because by flux insertion, if the filling factor is not integer, then you must end up with some different state from initial state. So this simple scenario of the trivial insulator actually contradicts with this exact statement, which means that if the filling factor P nu is fractional, that is non-integer, the system cannot be a featureless insulator. So that leaves two options. So this system may be either a gap, has a still gap, but in that case, there must be ground state jealousy because if you do this adiabatic flux insertion, you must end up with different final state, and the final state must be still ground state. So that means that there must be some ground state jealousy. So physically, this may be a signature of the spontaneous symmetry breaking or topological order. And another possibility is that the system may be gapless or massless in field theory language, which conduct electricity and so on. And this constraint holds in any dimension. And also, I didn't use the statistics of the particle. So this conclusion stands valid either for bosons or Fermi. So this is very universal statement. And this is called Lipschutz matrix theorem. It's a kind of generalized Lipschutz matrix theorem. So, okay, so yes. Value of flux? Yeah, so, okay, so yeah, to make, are you asking a particular value of flux or? Yeah. Yeah. So to say this, I'm assuming that that doesn't happen. So in principle, even if you had a gap at zero flux, the gap may close at some finite flux, then this argument breaks down. But yeah, physically, we believe that especially if the system has a gap, finite correlation length, the system shouldn't be too sensitive to the flux. But actually, directly proving that turns out to be very difficult. And as far as within my knowledge, nobody has really proved that statement. But on the other hand, this statement was proved by Hastings and other people directly without using this adiabatic argument. So yeah. Well, okay, yeah. So maybe in general, yes, but in if this ground state degeneracy is due to SSP or topological order, we believe that this degeneracy, well, maybe okay. Yeah, in general, it can depend, but well, so maybe what we can say is that if the system is featureless insulator, then ground state must be unique for any Ly. And this argument shows a contradiction with that statement. And actually, I forgot, maybe this mathematically more rigorous proof may prove this degeneracy for any Ly, but I don't remember. Thank you for. So that was very powerful result. But actually, on one hand, it's kind of intuitively natural once you get the idea, because as the theorem I just derived says that if you have integer filling, then you can realize featureless insulator. And in fact, if you have free fermion, then you have a band structure. And if you fill certain number of bands completely, then you have band insulator. And to have a band insulator, actually, you must have an integer filling. So this is consistent. And on the other hand, if you go to strong correlation limit or strong interacting limit, then you can also consider atomic limit, like each site is occupied by one particle. Then this can be insulator, trivial atomic insulator with a gap. So again, this is consistent. And now we can consider changing the filling fraction slightly from 1 to 0.9999 or something like that. And to do that, you remove small number of particles, like you remove this particle, then you create a hole in the system. Then now this particle, for example, can hop to this empty site. Then after this hopping, this hole, you can interpret this like a hole move to right. So actually this kind of procedure that is removing or adding a small number of particles to the system is called doping in solid state physics. And once you do the doping, this hole can become mobile. So now this hole can hop around. Then you can expect that the system should become a gap-based conductor. So intuitively, this result is kind of natural, but this flux insertion argument shows that this result is robust, does not depend on this simple limit, but it's more universal and holds for any strength of the interaction. But still, you might say, okay, but maybe trivial. Maybe you are right, but I would say maybe it's trivial once you understand, but before you understand thing, then it's actually highly non-trivial. Because I can mention one example. So we can consider this Heisenberg antiferromagnetic chain in one dimension. The interaction is just S dot S, and the interaction, this coefficient is just positive. And we can consider this system with a spin quantum number S. So this is actually exactly solvable for spin 1/2, but it's not exactly solvable for any other value of spins. So it's kind of non-trivial interacting system in one dimension. But we can map this system to system of particle because for spin S, Sz can take 2s plus 1 possible value starting from minus S to plus S, as you know. And then I can identify this Sz equals to minus S state as a vacuum. And then next possible eigenvalue is minus S plus 1. And I can interpret this state as I put one particle, so-called magnon, to this site. So then particle number is 1, and so on. So if Sc equals to minus S plus 2, then I put 2 magnons on the site, so particle number 2. So you can always make this mapping. So you can rewrite this Hamiltonian in terms of some interacting magnons, if you like. And now if you do this, then magnetization per site in this spin chain language is just the expectation value of this Sz. So expectation value of Sc, which often called M, is nothing but minus S plus particle number. So in terms of the filling factor of this magnon particles, this magnetization per site is minus S plus. Okay. And in this kind of antiferromagnet, it's generally known or proven that the ground state must have zero magnetization, M equals to 0. Which means that for spin S chain, in the ground state, this filling factor of this my particle magnon must be given by spin quantum number. So if you have spin 1/2, filling factor is 1/2, spin 1, filling factor is 1, and so on. So from this, and combined with this Lipschutz matrix idea, we can say that if the filling is integer, nu is integer, which is nothing but spin is integer, then featureless insulator gap state is possible. But if the filling is fractional, that is spin quantum number is 1/2, 3/2, and so on, then you cannot have a trivial featureless gap system. You must have some spontaneous symmetry breaking or gapless system. And actually, this corresponds to the famous Holden conjecture because, as I mentioned, many decades ago, it was recognized that the spin one-half chain case was solvable. Then people found a gapless spectrum. So most people assume that this model must be gapless for any spin quantum number. But then in 1981, Duncan Holden came up with a surprising prediction that this system is gapless only for half odd integer spins, like a 1/2, 3/2. But if you have integer spins, then you have a gap. That's a so-called Holden gap, which was at least an important part of his Nobel Prize in 2016. But anyway, back in 81, almost nobody took this seriously because it was so much against conventional wisdom in solid state physics. But if you make this mapping, these two cases are clearly different because the integer spins correspond to integer filling and half integer spins correspond to fractional filling, at least at the 0, 1 theta. So yes, well, zero magnetization pass in average, yeah. Not really, because each site I make this correspondence. So the magnetization is total SZ per site, but that's equivalent to expectation value SZ, assuming the translation invariant. So yeah, so by this example, I wanted to say that this Holden conjecture was very surprising back then, and so surprising that very few people took this seriously. But if you make this correspondence and apply this filling factor idea, then this difference is so natural. So in that sense, I would say this filling enforced constraint is still non-trivial in that. But of course, once you understand better, then things become simpler. I remember if you attended the physics night on Monday, Hiroshi Oguri, maybe it was Hiroshi Oguri, emphasized that some student asked that now you have to learn too many things, so how we can make a progress or something like that. And part of his answer was like, of course, physics also progress, but then our way of understanding also progress. So by simpler understanding, we can maybe hopefully go far. Anyway, okay. Mhm. Yeah, but if it's conserved, at least theoretically you can assign a fictitious charge for theoretical argument. As long as this total SD is conserved, yeah, I can introduce a kind of fictitious gauge field to make this argument. Okay. So I want to also mention some historical curiosity. So as I mentioned, this idea originated from this famous deep shoot Matisse paper back in 1961. And now this paper gets thousands of citations, mostly because of this deep shoot Matisse theorem. But if you go look this paper actually, then you find that this famous paper is actually not about this famous theorem, deep shoot Matisse theorem. Actually, this paper was mostly about the exactly solvable model of quantum spin chain. Actually, now in modern language, this is XY chain and some variant. So basically, you can solve so-called spin one-half XY chain by Jordan-Wigner mapping to free fermions. And nowadays, it became so standard that maybe you don't bother even citing this paper, but this is the first paper which applied this Jordan-Wigner to spin one-half XY chain, and they solved exactly. So this famous theorem actually was not even in the main text, so they discussed in the appendix B. So apparently, these people, even those authors themselves didn't think this theorem too important, but at least they included in this appendix. And if you look into this appendix, actually, so yeah, maybe I skip this. Okay, so then so in 61, so this Lipschutz matrix proved this only for spin one half XY spin one half chain. But as I mentioned, they solved the spin one half XY chain exactly, and Heisenberg chain can be solved by beta and that XXY chain. So maybe they didn't think this theorem too important because they could solve exactly these models. So they didn't even need this theorem. But and then after that, Duncan Holden made this Holden conjecture, famous one I already mentioned. And only after this Holden conjecture, Affleck and Deeb. So Deeb is arrow, this LSM. They discuss a generalization of this Lipschutz matrix theorem for general spin chain, and so then it got more interesting because it shows a interesting difference between integer and half integer chains. And then we generate this to general magnetization, then we could make a connection with more general filling factor idea of many particle system and so on, so on. So it has a long history, but even recently there are many interesting progress. So maybe there are field theory people in this room. So in terms of field theory, maybe it's already mentioned in some other talks in this conference, but this Lipschutz matrix theorem, in terms of field theory, is related to the two-foot anomaly or mixed anomaly in quantum physics. So yeah, then so I mentioned one particular application of flux insertion to put a constraint on the possible quantum phase in quantum many-body system, but there is a related application to gapless system. So if you consider fermions with generic fractional filling, then you expect a gapless system. And many of such systems are metallic and conductive, and they are not every one of them, but many of such interacting fermion systems are described by Landau's Fermi liquid theory. So in Landau's Fermi liquid theory, so original particles, fermions are interacting. So the original fermions are not well-defined excitation, but Landau postulated that even including interaction, you can define a so-called quasi-particle, which is very roughly speaking, fermion dressed by some interaction. And these quasi-particles behave like a free fermions. And you can still define the Fermi surface. And in terms of quasi-particle, quasi-particle near the Fermi surface behaves almost like a free fermions, even though it's dressed by interaction. Then you have Fermi C. Fermi surface and Fermi C. And in general, this shape of the Fermi surface can be renormalized by interaction. Okay, so if you have no lattice in the continuous space, by symmetry, this Fermi surface should form a sphere. Then it cannot change unless you break some symmetry. But in the lattice, the Fermi surface can take a different shape. But this shape of the Fermi surface can be renormalized by the interaction. But you can ask whether what happens to the volume of the Fermi C. And to answer what happens to the volume of the Fermi C, we can use this flux insertion argument. So if you assume the Fermi liquid theory, you have a well-defined Fermi surface. And if you insert this flux insertion induces electric field. And by applying the electric field, each quasi-particle is shifted to the next momentum. So each quasi-particle gains this particular momentum, 2 pi over Lx. So as a result, entire Fermi C shift to the x direction. then you can compute the total momentum shift due to flux insertion in Fermi liquid fixture. And the result is proportional to the volume of the Fermi sea in the momentum space, because the entire Fermi sea is shifted. And so this is the momentum shift in terms of the volume of the Fermi sea. But I already derived the exact result using this large gauge invariance, because this result does not depend on what kind of phase you are in, or what kind of interaction you have. So this is always exact. And this is exact as far as the system is described by the Fermi gauge. But they must be equal. So if you equate these two, then you find the result that the volume of Fermi sea divided by some factor must be given by filling factor, the particle density modulo 1. So this means that whatever interaction you have, as far as you have Fermi liquid, the volume of the Fermi sea is unchanged, and it's always given by the particle density. So this corresponds to the again, very old results, famous result in solid state physics, so-called the Rattinger theorem. But in the original theorem, you have to do some diagrammatic calculation. So basically, the original proof was based on perturbation theory, I would say. But by using this kind of argument, you can show that this is valid. This must be valid as long as the assumption of this Fermi liquid is valid. So yeah, then again, you might think, okay, so this Rattinger theorem was known since the 1960s, so what's new? But I would say, okay, so this may be even simpler. Again, simple is better, and also non-perturbative. And another interesting point is that same argument can be modified to be applied for non-Fermi liquids and also quantum lattice. So in particular, these people propose a concept of fractional Fermi liquid. So I'm not going into detail of this theory, but this is almost like a Fermi liquid, but has some topological nature, and this theory contains some topological vortex excitation. So if you apply this flux insertion idea, then in this fractional Fermi liquid, FL star, you not only shift the Fermi C, but you also create a new topological excitation, topological vortex. And this topological vortex carries certain momentum. And now, momentum shift due to the Fermi C shift plus this momentum carried by topological vortex must be equated to this exact result I can derive from large gauge invariance. So if you equate left-hand side and right-hand side, then now Fermi C volume is given by some filling factor minus 1/2. And this minus 1/2 factor represents a violation of the conventional Rattinger theorem. But in a sense, this is a generalized Rattinger relation, which can be applied to this kind of more non-trivial, topological non-trivial variation of the Fermi. So again, I'm not going into details, but this may be of interest because so you know this there is a high TC two-plate superconductor which was discovered in 1986, but even now theorists debate how to understand this system, and this FL star may be useful to describe some finite temperature phase of this material. But so yeah, I included this because I remember I gave a talk on this flux insertion derivation of Rattinger theorem back in maybe 20 years ago ish in KITP Santa Barbara. And there are several senior big shots in the room, and I presented this argument, and they were asking like, where's Feynman diagram? Because for some generation of condensed matter theories, theoretical physics was almost synonymous to theory of Feynman diagrams, but I was not using any diagrams. But yeah, I would say my approach, this flux insertion approach, is closer in spirit to the original idea by Landau on Fermi-Liquid theory, because Landau conceived this Fermi-Liquid theory idea without using diagram. That's a kind of assumption on the low energy effects. But after 10, 20 years, this approach became popular. Okay, so this is Subia Satyev's textbook, and he spends one section to explain this, how to derive this general Latinger relations. Well, so maybe he is biased because this is useful for his favorite FL star theory, but anyway. And it's also taught in a graduate course in Latvia, several other universities. Anyway. So I have maybe slightly less than 10 minutes, but so far I have discussed application of flux insertion and asked what is a momentum shift. And that was useful to derive this filling length force constraint or Lipschitz-Matisse theorem, and also this general Latinger relation. But I can also ask what happens to the energy, total energy, because the energy is also important quantity in physics. I can ask what happens to the total energy if I do flux insertion. So actually, we find that energy gain. Okay, so if you do flux insertion, in general, so let's say you start from the ground state, then energy was smallest possible value. So by doing this flux insertion, you can only increase the energy. But this energy gain during a flux insertion process turns out to be non-universal. It's different from moment, but still can be useful as follows. So that is because now let's consider the current operator. And actually, current operator or total current is defined by the partial derivative of Hamiltonian with respect to vector potential after including this vector potential. So this is a general definition of the current. So the current density or current per volume is obtained by dividing this derivative by this V, total volume of the system. Okay. So now I'm considering the flux insertion process in which the vector potential is proportional to the time t, at least during this process. Then this partial derivative by vector potential can be written like this. So this is the partial derivative of Hamiltonian by time divided by the rate of increase of the vector potential. So using this equation, I can say that the expectation value of this current density is proportional to the increase rate of the total energy. So expectation value of Hamiltonian is nothing but the total energy. So total energy increases by this flux insertion. And in fact, this increase rate is proportional to the current density. So using this relation, we can actually derive a useful result. So now we can consider the current as a response to the electric field. And often in condensed matter physics, people use the momentum space representation, the frequency representation, but we can also use a real time formulation like this. So that is electric field applied in time t prime can affect the current at time t, where t is bigger than t prime. So this is a causality. So applied electric field can only affect the current in the future, not in the past. So so now I consider this adiabatic flux insertion where vector potential is proportional to time and increase this vector potential over time period capital T. and I take this capital T bigger and bigger. This is the adiabatic limit. So if you take this adiabatic limit, then only the response with the infinite delay time will survive in a very distant future. So then we can consider the limit of this response function, real-time response function in the limit of infinite delay time, and write it's capital D. And then current at time t is proportional to this capital D times t, if you plug in everything. And I would say this D is nothing but Drude weight, another popular quantity in solid state physics. So in frequency space, Drude weight appears as a coefficient of the pole of 1 over omega in the AC conductivity. But in real time formulation, it's like. So now, as I said, the energy increase rate and the current density are proportional to each other. So now I can integrate both sides from time 0 to capital T, the end of the flux insertion process. Then if you integrate, then left-hand side becomes just an energy increase due to adiabatic flux insertion. And the right-hand side becomes some d times some quantity, t squared and so on. But if you equate these two, actually you can derive some equation for this Drude weight d. That is because you insert this flux adiabatically, you should always follow the ground state. So if you compare both sides, you find that this Drude weight d must be given by a second derivative of ground state with respect to the vector potential. And actually, this is another well-known, very famous formula in solid phase physics, that is Kohn formula for the Drude weight. So Kohn derived this using different argument, I think, but still he derived this in 1964. So what the point of the introducing this flux insertion is that now we can readily generalize this to, for example, to nonlinear conductivity. So these days, nonlinear response, nonlinear conductivities become important, partly because progress of experimental techniques. So now experimentalists can shine the laser to the material, then they can measure the effect of the strong electric field. So now I can generate this real-time response of the current to the electric field to higher orders. So at nth order, the response should look like this. Then again, there is a response function in real time. And by sending this delay time to all the delay time to infinity, I can derive the nonlinear version of the Drude weight. And yeah, again, I use the same logic because I have the identity between the current expectation value and the energy increase rate, and I integrate both sides. Then you can equate energy increase to the some higher order Drude response. And then in the large system, this change of the vector potential is small. So at the end of the day, we find that this very simple formula for nonlinear Drude weight, that is nth order Drude weight, is given by n plus first derivative of ground state energy with respect to vector potential. So if you put n equals 1, this is a familiar Kohn formula, but for any n, this is basically valid. So this is not, okay, so I'm running out of time, but just one last example. So to derive the Drude Kohn formula and its generalization, I use adiabatic flux insertion, but I can also insert this flux suddenly. Then, so it's like a quench process. You just switch on the flux. And in this case, quantum state cannot follow the change of the Hamiltonian. So this is a well-known case of sudden approximation in quantum mechanics or quench process. But we can still use this identity between energy increase to the current. But now this capital T, the duration of the flux insertion goes to zero. So in that case, we pick up the response, real-time response at zero delay. So at nth order, so we can again insert this nth order response to this formula, and at the end of the day, we can derive this kind of formula that is instantaneous response with zero delay time for nth order nonlinear conductivity is given by this simple quantity. That is expectation value with respect to the ground state. And in the middle, you have an n plus first derivative of Hamiltonian with respect to the vector potential. And this instantaneous response, if you go to the frequency space, is nothing but the frequency integral of this AC conductivity. So again, at n equals 1, this is very known result, so-called F sum rule, frequency sum rule of conductivity. But again, by using this flux insertion argument, I can readily generalize this to any order of nonlinear conductivity. And we check this numerically. So to summarize this part, okay, so this F sum rule and the Kohn formula nonlinear generalization looks very similar, but they are different because this corresponds to instantaneous process, sudden process, but this corresponds to adiabatic process. So two different limits of very similar flux insertion. Okay. So yeah, I ran out of time, so let me stop here. But I hope I could convince you that yeah, these thought experiments are fun and useful, and in particular this flux insertion argument, very simple but has many applications. Actually, I forgot to mention, but yeah, historically, first such example in quantum physics was a famous Laughlin gauge argument for quantized for quantum. But we have a bunch of other applications. Thank you.
Questions?
Thank you very much for the very nice talk. This is something I was thinking about like 2 or 3 years ago, but not anymore, not as much. But I have two questions. One of them is, are there like higher dimensional generalizations of these flux threading argument that you can make in like anomalous Hall, for instance, in biosemi-metals? And the second question is, because recently I read this article by Dan Sun and Duncan Haldane, in which they talk about this spectral sum rule that involves shift index, which I don't really understand what that is. But do you think it maybe that index also fits into this framework of like the filling constraint and stuff?
Yeah, maybe. Yeah, again, yeah, I maybe heard about their argument, but I also don't understand, so I cannot say much something intelligent. But to the first part of your question, so yes, so these results are valid for any dimension, but I have to admit that so far my argument only uses flux insertion in one particular direction, so which generates this electric field in one particular direction. So yeah, there may be some more clever way to generate this generate some electric field, gauge field in higher dimensional structure or something, but yeah, I don't know. So far I don't have a good idea. If you have a good idea,
Yeah, let's chat later.
Yeah.
Yeah.
Thank you.
In this argument, you need to have a one direction compactified. Does it can be generated a non-compacted space, or
Yeah,
crucial?
so yeah, I need to put the periodic boundary condition.
Mention some QFT. Is it
By non-compact means open boundary condition or
yeah?
Oh, okay. Yeah. And yeah, if there is one direction which is close, I can apply this. But if you have a Corbino, yeah, if you have edge, then these constraints may be satisfied by the edge state. So maybe I cannot say something directly on the bulk physics, but the argument itself is still valid if you have one direction which obeys periodic function.
Maybe if you modify to anti-periodical, does it
Yeah,
change?
this so anti-periodic boundary condition we actually used in some occasion, not discussed here. But for example, if you have a discrete symmetry, you can no longer use this flux insertion argument because the gauge field is no longer continuous. For example, Z2 symmetry. But you can sometimes derive a similar result by using the anti-periodic boundary condition. Yeah, a little bit off from my talk today, but the anti-periodic boundary condition can be used.
Thanks.
There's one quick question, and then we break for coffee.
Thanks for interesting talk. So in the relationship between this kind of argument and the more traditional Feynman diagram argument in the context of anomaly in KFT, that for the perturbative anomaly, there's a clear relationship between the topological type index theorem and the lowest part of one of Feynman diagram. So is there any kind? So I vaguely sense that there's a relationship between this kind of argument to the anomalies. I wonder whether there's such kind of relationship between your argument to the more traditional Feynman diagram calculation.
My argument to
So in the Latinger theorem,
yeah.
So you mentioned about the Feynman diagram, I really interested in the wonder whether there's the direct relationship between.
Oh, I see. So the perturbative interpretation.
In the context anomaly in KFT, the perturbative anomaly is clearly coming from the one loop diagram, and it is also a topological quantity from.
Okay. Yeah, good question. Okay. Yeah, good question. So yeah, thanks for the question, but I don't have a clear answer.
Thank you.
But an interesting question. Maybe we can discuss. Yeah, thank you.
Since the next talk starts very soon, let's thanks again.